Hello AP Chemistry and welcome to Chapter 6. The vast majority of what is in your AP book for Chapter 6 comes from Chapter 9 from last year, and it is essentially a review. So if you need to brush up on some stuff or you feel like brushing up would help your understanding, that's where you would look at your stuff from last year. So anyway, Chapter 6, there won't be a lot in terms of lecture because you already know most of this. So anyway, thinking in terms of electromagnetic spectrum, we talked about this last year already, and same thing applies. There is no expectation that you've memorized that RF, right, happens to run from 10 to the third to 10 to the negative 1 meters in terms of wavelength, right? But you do need to understand that as the wavelength gets, what direction is this? Shorter, right? Then we get higher energy wavelengths, right? As the wavelength gets shorter, we get increased frequency because the frequency is inverse because that's the number of waves in a 1 second window. And if the wave is smaller, clearly there will be more of them in a 1 second window, right? Note again, just like last year, right? The visible region makes up a terribly small part of the actual spectrum. And you should know this whole Roy G. Biv thing that you guys probably learned somewhere in grade school, right? And then I'll just help you to remember the ordering of the energy for that. And you should know some of the basic uses for some of these types of waves. Okay. Moving along, photoelectric effect. So your book also talks about black body radiation, which is also important and is one of the observations that helps to lead to the development of the current model of the atom. Photoelectric effect gets its own special mention because it is the foundation for photoelectron spectroscopy, which is one of the analytical methods that we're going to talk about in depth, and we'll spend a whole day talking about that and practicing how to interpret PES spectra. But anyway, so photoelectric effect. So here we have what is an open circuit, right? So we have a voltage source, right? So this is a source of electrons, right? That's what batteries are a source of electrons. We have a current indicator. So if current is flowing, this little bar here is going to move, right, to indicate that electrons are flowing indeed through the system, right? And here what happens is we have a metal surface and we have our terminal. But note that they are separated, right? This is an open circuit. There is nothing closing it. If you think back to 8th grade when you did with Miss Carroll, the concept of circuits, right? Everything needs to be touching, right? There needs to be a continuous metal loop in order for the electrons to travel all the way around, right? From one terminal of the battery to the other, okay? Here, that circuit is open, but instead, there is radiant energy, right? So any one of these types of wavelengths are being shined on the metal, right? And with the right energy of wavelength, we can get this, right? We can get some of the electrons to be ejected from the metal through space onto that positive terminal, thus completing the circuit. So even though those metals aren't touching, with the right type of energy, those electrons will be ejected, completing the circuit, and we will measure a current or a voltage depending on what we're measuring. Yes, does that make sense, right? Which means that, right, and the observation that was important in terms of development of the atomic model was that there was a minimum wavelength or there was a minimum energy necessary in order for these electrons to be ejected, right? So if your minimum wavelength was here, right, anything less than that was not going to see the ejection of electrons, right? So that part was really, really important. Also, there's a note in your book about how the intensity did not matter, right? Make sure you know what intensity is because that's going to play into our PES discussion in class. Okay. So then that brings us to the line emission experiments and the Bohr model, right? We talked about this last year, but just to refresh, right? We have hydrogen gas contained in a tube here, right? So this is hydrogen gas in an evacuated tube. We run an electrical current, so this part and this part are both plugged into electricity, right? We run a current through there. That provides energy such that the electrons in the gas are excited and it emits a pink glow, right? This one I believe is neon, right, which is red. And so just talking in general, if we take something that is a white light source, focus it through a slit, and then diffract it through a prism, we end up with a continuous spectrum, right? Like we talked about last year, right? This is a continuous spectrum where we see every single color. And important to note, right? Not just, but we literally see every single color, right? There's not even a break between red and orange, right? The wavelengths of red, there's a continuous change, so that way it subtly changes into orange. But it turns out that when we do this with hydrogen and we then focus it through a slit and then diffract it through a prism, instead of seeing a continuous spectrum, instead there are only 1, 2, 3, 4 lines that show up in the visible spectrum. There are a couple others that show up in the UV spectrum, but these are the ones that are observed in the visible spectrum, right? For neon, we end up with this set of lines, right? And so what that means is that when we take that light, we do not see every single color, which means that every single wavelength is not observed, right? Which again, Bohr eventually tied back to the concept of energy levels, right? Wherein we excite electrons by giving them energy, right? That electron absorbs energy and goes up to a higher energy level. It releases that energy in the form of a photon, right? And when it releases that photon, that's what we visualize. And that photon is the relationship between those two energy levels from which the electron was excited to which it relaxes, right? So basically, these 4 states are what's happening inside the hydrogen atom, right? Again, problems with the Bohr model were, right, it only worked for a single electron species. In between Bohr, there's de Broglie, which says that everything has a wavelength, right, including you and I as we walk down the street, but we don't appear to be moving in waves because, right, we are so large that our wavelength is so small that we do not appear to be moving in waves, right? Heisenberg said that every time we probe something, by default, we must exert some energy onto it, which means that we have moved it from where it once was. Again, doesn't apply to large things because we absorb photons constantly, or we are bombarded with photons constantly, and they do literally nothing to deter us from our path, right? But then that brings us to the quantum mechanical model, right? Important things to note there, right? Quantum mechanical model comes from the Schrödinger wave equation, which is why there are notations that are letters and numbers and things that are just weird, but that's where they come from, right? Do note that you should know that psi squared, right, is the electron density or probability density, or the probability of finding an electron in a given region, right? And where psi is just the wave function, psi squared is the electron density, right? The likelihood of finding it in a particular place, right? These are all different ways to represent an s orbital, right? So note that here, one of the key things about the dot density is nice is that it shows you, right, that this is the high probability region, which corresponds to this, but it's not excluding the fact that electrons can be found much further out than what the shell says, right? So bear that in mind, because a lot of what happens on an AP Chem free response, right, is here is an observation. Can you explain it using principles of atomic structure, molecular structure, something, right? And here, right, this is an important thing to note, right, that the vast majority of the time the electron is going to be close to the nucleus, but there are occasions where an electron will be found further out, right? So just things to note, right? Which goes back to here, if we look at these graphs, right? So if we look at the 1s, right, distance from the nucleus, this is the most probable distance, but we can find distances much further out, right? Note this is what again? Angstroms, right? For our 2s, right, we still get the same spherical model, right? But note that the vast majority are going to be found further out, so closer to 3 angstroms, where this one would be closer to 1 angstrom, right? But we do also have some density that goes very close, right? We have a node, and that makes sense because that's where most of the 1s electrons are. Yes, does that make sense? If most of the 1s electrons are at 1, right, then it makes sense that that's probably not where the 2s electrons are going to be, right? And we'll see that process repeat when we get to 3s, right? 3s electrons are most likely to be found at approximately 7 angstroms from the nucleus, right? And we get a node at approximately where the 2s electrons would be. We get a node at approximately where the 1s electrons would be, where the vast majority of those respective electrons would be, right? Does that make sense? Okay. All right. Here are the shapes of your p and d orbitals. You are expected to know the shapes of your p orbitals. There's no expectation that you know the shapes of d or f orbitals. You should just know they get more complicated. The thing to note, right, is that nuclear penetration decreases for each of the shapes as we get further from the nucleus, right? So s orbitals are likely to be closest to the nucleus, right? So even for 3s, right, we are still spending a significant amount of time, right, or there's still a significant probability that my electron is very close to the nucleus, right? Whereas by the time we get to our p orbitals, right, there is almost zero probability, right? Actually here, this one shows pretty clearly, right, that there is almost zero probability that it's actually going to be right at the nucleus, right? And you'll see for the D ones and the F ones, right, that's the same scenario that repeats, right? Okay, so then we get to our shells, subshells, and orbitals, which is what we talked about last year. So here, for a single electron species, right, this is the breakdown that we get, which is basically the Bohr model, right, where we have n equals 1, we have n equals 2, n equals 3, so forth and so on, right, and they can hold a certain number of electrons. And this is basically what we can envision for hydrogen, right? In that one electron, whether it's in 2s or 2p, doesn't matter, it's the same energy. Because what's unique about a single electron atom that is not true for every other atom? Right, there are no other electrons to create repulsion, right? So in a single electron atom, the only thing we're thinking about is that single electron and its attraction to the nucleus, right? Once we start to throw in other electrons, then we're also trying to deal with or trying to explain, right, the repulsion that happens between the electrons in addition to attraction to the nucleus, right? And that's when we get the splitting that we should all remember from last year, right? In that 2s is lower than 2p, 3s is lower than 3p, right? And in an anomalous sort of way, 4s is lower than 3d, which is lower than 4p, right? So forth and so on, right? And again, all of that ties back into exactly how the periodic table is constructed, so there's not really anything special that you have to remember there, right? Your book does provide that nice figure of the expanded periodic table, which shows us our S block, our P and our D and our F all stuck together, right? And it gets unwieldy and large, which is why we don't write it that way, right? But s orbitals, right? There is one s orbital holding a total of 2 electrons, which is why it makes up 2 groups, right? F orbitals, total of 14, right? D's are a total of 10, P's are a total of 6, right? And writing electron configurations, right? So the period number corresponds to what piece of information, going back to last year? Right. That corresponds to your valence, right? So all the elements on this period, their valence is 6, right? Group number corresponds to, right, group number corresponds to, or depending on how you look at it, right, the total number of valence electrons, right? So this means 4 valence electrons, right? So if we were going to write the electron configuration for lead, right, we would go to the noble gas before it, which is xenon, right? And then we would go 6s2, and then we come over here. Oh, we passed all of that, so that would be 4f14, and we passed all of that, which would be 5d10, and then we're 1, 2 into the p block. Yes? And that would be lead's electron configuration. Yes? Okay. Just some further examples. Right here you have your noble gas notation or your condensed electron configuration. Here, this is like some hybrid between condensed and orbital notation. If you are specifically prompted for orbital notation, this is what they want to see. They want to see, do you understand that the electrons, right, showing that last quantum number, right, are opposite facing arrows? And do you understand the Hund's rule where they are distributed across your degenerate orbitals? That's usually what they're looking for if they ask you to do an orbital notation. Okay, all right, that's the end of chapter 6, which will then take us into chapter 7, where we talk about periodic properties that arise due to the configurations of our respective atoms. All right, thank you for listening, be good, and I will see you soon. Bye.